All right, so here we go. So this video is going to be fairly similar to the last one in that it's basically going to be the Angular equivalent to stuff we already know. But I'm actually going to do a couple numeric examples in this one to show you a couple things. All right, so let's get going here. All right, let's begin, why don't we? All right, so angular momentum. All right, so a few chapters ago we learned that if an object is moving, it has what we call momentum. And the momentum of an object is equal to its mass times its velocity, right? It's sort of a measure of how much motion we have, right? The velocity is how fast it's going. The mass is how much we have, right? Okay, so it turns out that similarly, if you have a rotating object, that has what we call angular momentum. And I don't know why I'm missing a little quotation mark right there. All right, and as we learned in the last chapter, a lot of the angular stuff uses the same equations as the linear equation stuff. So the angular counterpart to mass is rotational inertia. The angular counterpart to velocity is angular velocity. And the angular counterpart to momentum is angular momentum. So the equation is exactly what you would think it is. So two quick things about that before I go on. So thing one is our units are going to be different. This guy has units of kilograms times meters per second. This guy has units of kilograms times meters squared per second, and I will explainify that here in a minute. All right. So the other thing I need to point out here is this. Angular momentum only has meaning with respect to a specified origin, okay? In other words, what's your pivot point, basically, right? What's your axis of rotation, all right? And so you can see that because, remember, our rotational inertia also depends on that axis of rotation, okay? I actually wish I used the term axis of rotation instead of origin there, but so you get the idea, all right? Or if you don't, you know, you can ask me. All right, so to calculate your angular momentum, you multiply your rotational inertia, I, about whatever your pivot point is, about whatever axis of rotation is, times your angular velocity, okay? And then similar to momentum, remember, when you multiply mass by velocity, that's scalar multiplication, so the direction of the momentum is always the same as the velocity. Similarly, the direction that your angular momentum vector points is always in the same direction as the angular velocity. All right, and remember, for us, that's just going to be basically be clockwise or counterclockwise. All right? All right, so what do we do with all this? Well, so let's take a quick look at the stuff we've learned. So kind of like last time, every one of these linear equations has a corresponding angular equation. All right, so we've already talked about this top row. Momentum is mass times velocity. Angular momentum is rotational inertia times angular velocity. So let's write out our things. So it turns out if your net force is constant, then your change in momentum is mass times change in velocity. That's equal to net force times time. Okay, the angular counterpart to that becomes this. The change in angular momentum, I wonder if you could call that angular impulse. I've never heard anybody call it that, but I guess that's really what it is. So anyway, your change in angular momentum is equal to, instead of mass times change in velocity, it's inertia times change in angular velocity. And instead of net force times time, it's net torque times time. Okay? You know, back in honors, we did a bunch of stuff like this. Mass times change in velocity equals net force times time if your net force is constant. So now we're going to do stuff like this. Inertia times change in angular velocity equals net torque times time. Okay? Be careful to make sure your torque and your time symbols look different. All right? Please note this only works if your net torque is constant. All right? So then what happens if, linearly, what happens if your force isn't constant? Well, then we can't just multiply force by time. We have to take this integral, right? So your change in momentum, so this is if your net force is not constant. All right? And I am right now realizing I forgot my little net symbol there in front of my force. All right, so change in momentum is, sorry, I got a little sloppy. So here, this is supposed to say the integral of net force with respect to time. Okay, and so the angular counterpart to that is that change in angular momentum is the integral of net torque with respect to time. Okay, and we also learned that net force is the rate at which your momentum changes. Net torque is the rate at which your angular momentum changes. Okay. And then these last two, we've already talked about these this chapter, right? Okay, but again, it's just sort of re-emphasizing that idea that every linear equation that we learned, at the beginning of the year, has now its own sort of angular counterpart. All right. So let's do a couple examples here. I think we're largely going to focus on this, and in the next video, we're going to learn about conservation of angular momentum, and we'll dig in a little bit more. All right. All right, so this first one says find the angular momentum of a 0.08 kilogram meter stick which pivots about one end at 0.25 hertz. All right, so the idea is we've got this meter stick like this, and it's going to pivot about one end. All right, and it's got a frequency of 0.25 hertz. So every second, so that's 0.25 rotations per second, right? So 1 second, 2 seconds, 3 seconds, 4 seconds, right? Ooh. All right, so let's do it. So the angular momentum of our meter stick is I times omega. Well, let's see, I for a meter stick, remember I is a rod and it's rotating about one end. So it's 1/3 mr squared where, so here's our meter stick, here's our axis of rotation, r is the length of the whole thing, okay? So our rotational inertia is going to be 1/3 times 0.08 kilograms times our radius, which is 1 meter. Don't forget to square it. And this gives you 0.026 repeating kilogram meters squared. So there is the rotational inertia of our meter stick. All right. Now, that meter stick, according to our problem, is rotating at a certain frequency. Now remember, frequency basically measures the same thing as angular velocity, right? So our angular velocity here is 0.25 hertz. That's rotations per second. But in order to call it angular frequency, we got to convert to radians. You have to do that. When you use this equation, all of these angular equations assume radians. Okay? So let's see, one rotation is 2 pi radians. If you multiply this out, it gives you 1.57 radians per second. Okay? So now we can find our angular momentum. L equals I omega. So our rotational inertia is 0.026 repeating kilogram meters squared. Our omega is 1.57 radians per second squared. Nope, no squared. Sorry, my bad. Boop, boop, boop. Multiply it out, and it gives you 0.0418 kilogram meters squared per second. And again, those radians, as they tend to do occasionally, kind of magically disappear. One of these meters in here is really meters per radian. Okay, so there's the rotational inertia of our meter stick. I'm sorry, no, there's the angular momentum of our meter stick. Okay? All right, so that's that. So finding the angular momentum of a rigid object like a meter stick or a wheel or anything like that is pretty straightforward. It's just I times omega. All right? We can also talk about the rotational inertia of a point. Okay? Now this is a little bit tough to see. And the next video is about conservation of momentum, conservation of angular momentum. So how do I want to explain this? So let's go back to that meter stick example, all right? So here's my meter stick. Right now it has no angular momentum, right? Now here's my finger. So my finger, hopefully it's on the screen here. So my finger represents a particle. The particle is going to be moving towards the meter stick, and it has angular momentum, even though it's not moving in a circle. All right, so what we're going to do is we're going to talk about the angular momentum of this particle, my finger, about this pivot point, okay? And so it turns out that, well, I'm getting ahead of myself. So that's what we're going to talk about. We're going to talk about the angular momentum of this particle about some fixed pivot point. Boop, 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 okay? So how does that work? All right, so here we've got a pivot point. It says find the angular momentum of the 0.25 kilogram particle. Oh, 0.25 kilogram. So here's our particle. All right, and it's traveling along this way. It's going to follow this dotted line at 2 meters a second. All right, and we are going to find its rotational inertia about this pivot point up here. Okay? So to do that, so let's see, L is equal to I times omega. So let's see, so I, remember, it's a particle, right? So I for a particle is just mr squared, right? And it doesn't really have any angular velocity, right? And so what we do is we kind of project, like eventually it's going to get to over here, right? And so what we're kind of doing is we're thinking about, all right, well, what if it was traveling in a circle at this instant? Going around in a circle like this, right? Okay, so when it got to that point, at this point, it would have an angular velocity of v over r, where this is your radius. Oops, I guess I should use a capital R again. Okay, so I'm going to replace my omega with v over r, all right? So, but notice here, this is a little bit weird, okay? So r is, how do I want to explain this? So r is the radius from the particle to the pivot point, but you just measure the component of that distance perpendicular to the velocity. All right, that took way more words than I needed to. When you measure your radius, you always measure the radius so that it is perpendicular to your velocity. All right. The reasoning behind that has to do with the fact that there's a cross product hidden in here and math stuff happens, all right? So the idea is like some of you are looking at this and you're going, wait a minute, isn't this the radius? And the answer is no. What we want to do is we want the component of the radius that's perpendicular to the velocity. And since my velocity is horizontal, my radius has to be measured vertically. So that's my radius, okay? So I will give you a visual of why that's true in just a second, okay? Okay, so anyway, so let's plug in our numbers now. So, so when we finish simplifying this, let's see what happens. So r squared over r gives you r. So this basically simplifies down to mvr. I'm mad that I chose a capital letter R here, because usually I use lowercase letter r. But anyway, you'll be good, all right? So this is how you find the rotational inertia of a point particle. Is you just do mvr. So for us, the mass of our particle is 0.025 kilograms. The velocity at which the particle is moving is 2 meters per second. And the radius that it is away from our pivot point, again measuring that radius perpendicular to the motion, is 0.8 meters. Multiply this mass out, and you get 0.04 kilogram meters squared per second. So there's the rotational inertia of that particle. All right, so let me convince you about this a little bit, all right? So why do we measure the radius that way? So let's go back to this idea of the meter stick and the particle, right? So in the next video, we're gonna learn about conservation of angular momentum. It's similar to conservation of regular momentum, right? So if you've got like a billiards ball and another billiards ball, boom, right? When they collide, the first one stops, other one starts moving, right? Because the momentum of this one gets transferred to this one, but the total momentum shouldn't change, right? Okay, so same idea with angular momentum. So check it out. Right now the meter stick has no angular momentum. So here's my finger moving. So here comes my particle, right? So check it out. Right now my radius, remember the radius is the distance from my pivot point to where the particle is going to kind of hit, right? So check it out. I'm going to move my finger really slowly. Oh, that barely gave the meter stick any angular momentum, right? Okay. Let's increase my radius. I'm going to move it down here. Whoa. See how much that moved the meter stick? Okay. As opposed to this, right? So the idea is this has way more angular momentum about this point because it's farther away. All right. And some of it has to do with torque. Some of you are probably thinking, oh, well, it's just a bigger lever arm. And yes, you're right. There's definitely a connection there. It's a little bit deeper than that, but if you're thinking along those lines, then yes, you're absolutely barking up the right tree. Okay, so, all right. Okay, so next, so let's talk about this. So a few chapters ago, we talked about this at the start of the video, right? This is that change in momentum is net force times time thing, or integral of force with respect to time, right? So our new angular counterparts for that are this and this, right? Okay, so similar to angular momentum, change in angular momentum only has meaning with respect to a specified pivot point. All right, and it's always in the direction of the change in angular velocity. That's all pretty straightforward, I think. All right, so now the problems that you're going to need to solve are, well, before we learned that if I gave you force at time t, here, I'm going to set this up the same way I did in that last video. So linear, angular. So for linear, we learned that if I give you this, that you can find your change in momentum by taking the integral of 3t squared plus 4 with respect to time. So your starting time is whatever, maybe 1 second, ending time is 5 seconds, right? I totally didn't give myself enough room there, all right? So that's a thing that we would have done before, right? So now our new angular counterpart for that is going to look like this. Maybe I'll give you, net force, net force. All of these forces should be net because net force causes your change in momentum. All right, so similarly, net torque, if I tell you that's 3t squared plus 4, then to find my change in angular momentum, I'm going to integrate that with respect to time. Okay. Graphically, that would be area. Did not give myself enough room here. Let's see. Whatever. All right, so for number 2, if I give you a graph, force versus time, then the area is the change in momentum. Again, net force, I don't know why I can't remember that. All right, over here, net torque versus time. Your area is going to be your change in angular momentum. Okay, so the problems you're going to see are really similar to these, except it's all angular. All right, so that's 1 and 2, and then 3 and 4 are about the derivatives. All right, so number 3, so, oh shoot, what was I using? Blue, okay. So maybe I give you this. The momentum of an object at time t is 3t squared plus 4. Oh, that means my net force is the derivative with respect to time of 3t squared plus 4. So what is that, 6t, right? So now my new linear equivalent to that would be this. The angular momentum of a thing is 3t squared plus 4. Oh, that means that the net torque is the derivative with respect to time of, oops, I put an extra equal sign here. Hide that, we'll make it into parentheses. All right, of 3t squared plus 4, which again gives you 6t, right? Okay. And then graphically, it would just be the slope, right? If I give you a momentum versus time graph, the slope is net force. Over here, if I give you an angular momentum versus time graph, the slope is net torque. Okay? So again, the difficulty of those types of problems are going to be pretty straightforward. Okay? So I think that's it for this one. Yeah, look at that. All right, cool.